This talk is going to really focus primarily on superhydrophobic materials, but I will also look at other ways in which you can make material surfaces which have unusual properties. Hopefully I've got a few videos which will come forward and you'll be able to get the gist of what I'm talking about. But really the focus will be looking at surfaces that self-clean themselves or are very resistant to abrasion and staining. So this can go from everything from clothes through to pipes, through to surfaces like windows, and there's a variety of different potential functional applications. So on this particular slide, you can see an ant rolling a water drop, and you notice that the water drop is nearly spherical in shape, and that's because it's on a surface which is superhydrophobic. So this is a surface which is ultra water repellent, and the water droplet has a near marble shape on the surface. And this is related to an effect known as the lotus effect, and this is an example of a lotus leaf with water droplets on the surface. And when you have a surface which is very highly water repellent, water moves on that surface in a rolling motion, and that rolling motion helps to pick up dirt, dust, viruses and clean the surface. Now, to generate a superhydrophobic surface, you need two things. You need to have a surface which is intrinsically rough, and you need to have a surface which has a low energy of interaction with water. So there's a chemical feature and there's a surface roughness feature. And when you combine both of these together, you can generate a superhydrophobic surface. So in addition to self-cleaning, some of the other applications for these surfaces relate to anti-icing. So it's possible to have surfaces which delay icing in very cold environments if they're superhydrophobic. You can get spectacles or glasses that don't mist when you go from a cold to a hot environment. And also you can get a drag reduction and potentially reduction in biofouling of surfaces, both for conventional everyday surfaces, but also surfaces relating to gullies and pipework. So to start with, I'm just going to have a few definitions of what's meant by hydrophobic surface. So a hydrophobic surface has a water contact angle which is greater than 90 degrees. And this is the angle here subtended with the surface. So you see an angle going up here. This is this angle theta. It's hydrophilic if the contact angle, well, in some definitions less than 60, but the one I'm using if it has a contact angle less than 90. And it's superhydrophobic, similar to the structure we showed with the ant, if the contact angle is 150 degrees or greater. Now there's some other angles which are also important for these superhydrophobic surfaces. One is the tilt angle. That's the angle in which the droplet will roll on the surface. We also have the advancing and the receding contact angles as well. So that's hydrophobicity. It's also important to have a few other things in your mind as we go through the talk. One is I'll talk about omniphobic coatings, and these are coatings which repel both oil and water, and oleophobic coatings which are oil repellent. In addition, I will talk about slips surfaces, which are slippery liquid infused porous surfaces, and just to note that a superhydrophilic surface, which is one which is water loving, will have a contact angle less than 10. Now, to have a self-cleaning surface, you either want to be superhydrophilic or superhydrophobic. If you're superhydrophilic, and this is an example with commercial window glass, such as Pilkington Active, that has a titanium dioxide layer on the surface, and when activated with sunlight, any water that impacts on the surface will form a sheet, and that sheet washes down dirt uniformly. If you have a superhydrophobic surface, the water on the surface forms a ball and it rolls across the surface, and this surface motion helps to give you the self-cleaning activity. Now, for superhydrophobic materials, the commercialization of that has been relatively limited. And the reason why it's been limited and the major challenges in this area are down to surface robustness. That is, the rough surfaces that you need to generate the superhydrophobic surface are very readily abraded with any mechanical shear force. So for example, the majority of artificial superhydrophobic surfaces, if you were to rub them with a tissue, you would remove the superhydrophobic surface because you will remove this surface roughness microstructure. Another problem is oil contamination on the surface. If the surface gets contaminated with oil, it doesn't then behave as a superhydrophobic material. And so these are some of the two main challenges in the area in terms of commercialization. Now what we've done is to develop a new form of making superhydrophobic surfaces. And the way in which we've done that is to take two different types of nanoparticles of different sizes. If we combine them together and we put them onto an adhesive layer, now this adhesive layer can be as simple as double-sided tape, but it could also just be a spray adhesive. What we do is that we reduce the amount of abrasion that happens when you rub the surface. And so instead of rubbing off the surface features, what happens is that you push the surface roughness into the elastic or polymer layer, and it then, as soon as you take the shear force or the force off, it then pops back out. So instead of rubbing off the surface, you just push the surface into the elastic layer, and that gives rise to a high degree of stability. And in fact, this is something which we published in Science in 2015. It's a very simple idea, but just by either spray dip coating or syringe extrusion of our dual scaled nanoparticles onto a surface which we've already got an adhesive layer creates a very stable superhydrophobic surface. It's one that you can even rub with sandpaper 40 or 50 times and it will still function. This shows a TEM and SEM images of our surfaces with the rough microstructure. And over here you can see what happens when you put the water droplets onto those surfaces for both glass, steel, cotton and paper. And I will show, hopefully if I get it to work, some videos which relate to that. But if you have a superhydrophobic surface, oops, if I can get that to play. No, there we go, I think. Fortunately, we've got something else that comes up. I don't know if it's possible to... There we go. So this is our coatings which have not been treated with a superhydrophobic surface. And I'm dropping water droplets onto cotton, paper, steel surfaces. And you see that the water droplet just splats onto the surface. However, if it's superhydrophobic, it's very, very water repellent, and the water droplet, in this case it's been dyed with methylene blue dye, bounces on the surface, and even cotton, which is very difficult because it can absorb the force as you drop the water droplet, will actually bounce on these superhydrophobic surfaces. So they're the ultimate in water repellent when you have this material which is coated with something which is superhydrophobic. And the way in which we did that is just use this dual scale roughness of different nanoparticles in combination with an adhesive backing layer. So this gives you an illustration of what it looks like when we have a big syringe full of water which we then drop on the surface. The white coloured material has been coated, the bits to the side haven't, but you can see the water droplets will all bounce on these surfaces as you push them down. Now you can actually work out the number of bounces of water droplets on the surface and correlate that with the shape of the water droplet on the surface. And so there's a kind of kick-in point at 150 degrees which corresponds to a superhydrophobic surface where the water will start bouncing on that surface. And it will also have a rolling motion as the water droplet moves across the surface. And you can see on these particular surfaces we have a contact angle of about 160 degrees C. I'll just let it run on for one more bit as we'll have a little raster across the surface. So that's an illustration of a superhydrophobic surface and how it interacts with water and the fact that water doesn't wet the surface. Now you can also make materials as well to be very resistant to dirt or dye. So here we have a solution which has a methylene blue dye, which is a very strong staining agent, and we're going to dip into that solution the superhydrophobic cotton wool which we've made. So we've taken cotton wool and we've treated it with our superhydrophobic material. So when we put it into the solution of the dye and take it out, it's absolutely pristine, and so it doesn't undergo any wetting of that material at all. And this shows the rolling motion of the water droplets on the surface. So here we have a water droplet on a dust-covered surface, and the water droplet, as it moves across the surface, picks up the dust which is associated with the surface. And this is noted, this kind of acts as a miniature vacuum cleaner or a miniature Dyson, with the rolling motion picking up bits of dirt and dust, and in the natural world, bacteria, as it happens. Now, our superhydrophobic material is very resistant. It can withstand both finger wiping, sandpaper abrasion with a weight, or knife scratching and scissors, and it still shows and maintains its superhydrophobic properties. Now, the second challenge which I mentioned was related to what happens if you have oil contamination. Now, if you have oil contamination of a superhydrophobic surface, it normally kills the superhydrophobicity. But there are two ways in which we can use this. One is to accept it and take advantage of this, for example, for oil-water separation, and I'll give some examples of that. And two, we can refuse it and design omniphobic coatings. And this is where the slippery, liquid-infused, porous surfaces comes from. So the slip surfaces are actually superhydrophobic surfaces that have been treated with a lubricant. And if you put a very, very thin lubricant layer onto your superhydrophobic surface, you can make that surface resistant to virtually any form of staining. So what we're going to have a look first is to take advantage of this for oil-water separation. And the idea here is to make a membrane. In fact, we can do the membranes two ways around. We can have a membrane which will accept oil and repel water, or we can have a membrane which will accept water and repel oil. And so you can do them both ways round, depending on the kind of material you're looking at. And what I've got here is a series of videos where we're going to put in a superhydrophobic bucket, and we're going to use it to collect the oil which is sitting in this beaker. So you can see a side view and a top view, and this corresponds to oil which we've dyed. This is a light mineral oil, and you'll see, hopefully, if it works, that the oil will be absorbed into the bucket. Oops, oh, there we go. So here's the video. This is our bucket. And the bucket has a membrane, and the membrane has on it this coating which is superhydrophobic but super oleophilic. So it loves oil and repels water. And you can use that for abstraction of oil from the surface. So here we have, after 2 minutes, we've collected all of the oil from this particular beaker. And you can see it's all in the collection jar, showing very, very clean separation. So we can get something like 99.5% or even higher separation using this kind of technology, and also using it to separate out liquids from water from a variety of different media, even if they are very coloured. Now, the second challenge is what happens if we refuse it and we design omniphobic coatings, such as the slippery liquid-infused porous surfaces. So the way in which we do that is to make our superhydrophobic surface, and then we add a small amount of lubricant onto the top of that surface. Now, our lubricants actually are materials which are very high temperature lubricants. They operate up to 300 degrees Celsius. Some of them are fluorinated, some of them are not fluorinated. But when you do that, you generate a surface which is very slippery to everything. Now, we've looked at these surfaces with oil, tomato sauce, ketchup, mustard, wine, alcohol, a whole range of materials, and they actually will, if I can get this to work, oops. So this is showing repellents to oil and ketchup of the surface. So this is corn oil on the surface, and you see with this oil it will not stick to the slip's surface and will run off very readily. And we also do a little test with ketchup from McDonald's, and this is McDonald's ketchup on our surface, which again will run off the surface and won't stick to it. And you can coat a variety of different materials using this kind of approach to be repellent to oil and to water and to a variety of other materials. Now, these coatings tend to be, they're easy to treat, they're very mechanically robust, so you can actually put them under high pressure and they will still function. You can cut them with a knife and they tend to self-heal and still function as slips surfaces. You can cool them down to liquid nitrogen temperature and then warm them up to room temperature and they still work. You can heat them up to 200 degrees C and they still work. You can leave them for 3 or 4 months and they still work. Eventually, over long time periods, the lubricants will evaporate, but the lubricants we've got tend to actually stick to the surfaces for a huge amount of time. And also the surfaces themselves are very resistant to both acid and alkali. So they can withstand pH 0 or pH 14 for fairly long time periods before they actually show any degradation. So this is an example here with some liquid nitrogen testing where we took our liquids, we froze them into liquid nitrogen, we took them out, let them warmed up, and then they dropped off the surface. And similarly, you can put them on a hot plate at 200 degrees C and it also recovers its properties. This shows water, coffee, red wine and corn oil, which we've looked at, and the contact angles for hysteresis associated with these materials. And it also shows the particular cycles which we've done through the contact angle cycles as we've run through the material. And here, this is an illustration of the contact angle hysteresis associated with our particular coatings. So for both water, coffee, red wine and oil, they were very resistant to both of those materials, and we could remove the lubricant layer and then re-add it and it would still function. It's very strong in terms of resisting mechanical force, so this shows what happens when we put knife scratches across the surface. And we also applied a Newton meter to pressurize the surface and press things down. But again, although we did, as you increase the pressure, the sliding angle increased, we could still have very low sliding angles at relatively low pressure. Once you start going above this point here, which is about 800 kilopascals in pressure, the properties start to degrade a little bit, but you're still getting the very slippery type surfaces. The surfaces are also very corrosion resistant to both acids and bases, and we've done tests where we've had a metal base coat which we then overcoated with our slip surfaces, exposed them to both acids and bases and show no degradation of the underlying material. And we also get really good repellents here, so that neither the superhydrophobic coating or the lubricant is actually dissolved by the acid or base. We're really taking advantage of the ability of the lubricant to resist both acids and bases in this process. And as I've already said, it gives rise to very chemically durable materials. So we can also get the surfaces to be water repellent in oil. So this is dropping water droplets into an oil beaker, and it shows that the water doesn't wet the surface for our superhydrophobic surfaces. And it's also water repellent after being contaminated with oil. So here we have one of the surfaces which is being contaminated with oil. It's taken out, and then we're going to run down there some water, which I think is coloured. And you see that we get a surface where you can't actually stain the surface, but it easily runs off. So we're not getting the very high contact angles once it's been coated with oil, which we have for the superhydrophobic surface, but by having the oil there, it develops a slips type process where the oil will run off, sorry, the water will run off the oil infused surface. This just gives you an idea of the surface robustness test. And this takes quite a long time, this video, so I'm not sure I want to play it all. But basically, what you can see is that we have our superhydrophobic surface, so we're repelling water. And then the next test that's going to be done is, well, it's kind of our version of an SI test, is to put the surface down on filter paper. We add 100 gram weight to the surface, and then we travel across the surface. You will see there's a little bit of white scarring here, so we actually are losing a little bit of material as we do the traverse, but we can do this process up to 40 times and it still maintains its superhydrophobic nature. So this will be unloaded, and then you'll see that the water droplets will also bounce and run off the surface. So it shows that we've made a material which is very rugged. And you can also do underwater self-cleaning test. So the superhydrophilic coating was put underwater, and this time we're using oil. In this case, it's a hexadecane droplets on the surface. And you see that the hexadecane droplets, even in the presence of water, will not wet the surface. So you can have an underwater oleophobic nature associated with these particular surfaces. And you can also use the surfaces for fluid guidance. So basically what we have here is a surface in which we have, it's largely superhydrophobic, but we've actually, by using a UV kind of mask system, we've made a pattern on the surface, and you can actually get water to travel in predetermined directions. We've also developed systems where you can actually raise water up, similar to what plants do using the superhydrophobic system. Similarly to capillary action, you can actually raise water up by about 4 to 5 centimeters. So this is our pre-patterned shape. And you see that the water will wet some parts, but won't wet other parts of the surface. And you can end up with quite distinct patterns and get water to flow in particular directions or channels by having a superhydrophobic surrounding, but having the middle part which isn't superhydrophobic. Now, some other applications for these surfaces are to look at developing superhydrophobic paint. So we've made some superhydrophobic paint, and there's kind of some mixtures here. This is made with titanium dioxide and a fluorinated hydrocarbon, which when we just combine them together to effectively get a paint, which we can then paint onto the surface to make a superhydrophobic surface. This generates water contact angles of about 160 degrees, and this is an example of water rolling across the surface and picking up dirt and bacteria. But you can also use it to enhance the buoyancy of a material. And we've done a couple of little cheeky experiments here. One is to make little miniaturized boats, which are about 10 centimeters long. These boats we've coated with our superhydrophobic material. When it's coated with a superhydrophobic material, the boat floats higher on the water. And if we then do a test where we look at the speed of the boat moving through the water, we can see that we've got a definite drag reduction once coated with our superhydrophobic coating. So the boat moves much faster for the superhydrophobic coating, of the order of about 15 to 20% faster than it does on an untreated boat. We've also looked at taking a glass slide and loading it up with various metal pins or weighting. Now the glass slide on its own with no superhydrophobic coating will sink. We've looked at what happened if we just coat the edge, the top, or the whole surface, and looked at the degree of loading that we can get to. And we can have a depression of the water by about 4 millimeters or 5 millimeters once it's loaded with all these materials. Part of that is because the superhydrophobic coating traps a layer of air at its surface, but also due to the water repellency with the superhydrophobic coating. So this is something which nature uses for things like pond beetles and for water striders. It's how they can sit on top of the water. Their feet are very superhydrophobic, cover a large surface area, and enable you to have an overall higher buoyancy in the system. So we've done that for our superhydrophobic coatings, and this kind of illustrates what's happening at the edges of the coatings for our superhydrophobic material, where we're getting repellents of the water at the edges of the material. Okay, I wanted to move tack now and then to look at what happens if we were to make surfaces which not only could have superhydrophobic properties or superhydrophilic properties, but could also be used to kill bacteria and stop biofilm formation. And so we've helped to develop a series of photosensitizer coatings for antimicrobial applications. Now, one of the big motivations for this is to try and make surfaces which could be used, for example, in hospitals. If you go into a hospital, you have about a 1 in 16 chance of picking up a disease from the hospital if you're admitted as a patient. If you're a catheterized patient, you have a 10% chance per day additive of getting a hospital-acquired infection. So the really nasty end of this are things like E. coli and MRSA, and they can really cause problems for people because if you're in an immune-suppressed situation, or even for a healthy individual, it can be fatal in some instances and very debilitating. What we've tried to do is to develop coatings which will kill microbes or stop microbes from forming a biofilm. And the way in which we've done that is to use photosensitizers. So we've used light for this to create an excited state of a dye which has been incorporated into the surface. And this antimicrobial surface will kill bacteria when you shine light on it. So it will kill bacteria on contact. We've also shown in some systems where we can actually remove existing biofilm. So if you have a biofilm formed on these surfaces and you're to shine light on the surface, we're able to actually destroy the microbial surface. Now, the way in which light interacts with dyes to generate species which can be antimicrobial, in our case, is to have our substrate, and it can go via a type 1 or a type 2 mechanism. Type 1 mechanism is where you have incoming light, and that incoming light takes the material to the dye to its excited state, and through an intersystem crossing and then either phosphorescence or internal conversion and mechanisms in which it could lose its energy, you can actually take this excited state, and the excited state will react with substrates in the environment, could be, for example, water, to create hydroxyl radicals, or it can be from things like triplet oxygen and convert it to singlet oxygen. And singlet oxygen is very, very reactive and is able to destroy bacteria. So for the lethal photosensitization of microbes, what we've done is to make our antimicrobial paint, so it's very similar to what we've done before for our superhydrophobic surfaces. And in fact, we have made superhydrophobic surfaces which are also lethal photosensitizers of microbes. So to do that, we've incorporated a light-activated element. It can be titanium dioxide. It could be a dye or a photosensitizer dye. When we've done that on our painted surfaces, we found that bacteria find it A, difficult to stick to the surface, and B, we can generate reactive oxygen species when we expose them to light, even just very weak light, which is what you would get in an indoor environment. This generates our reactive oxygen species or singlet oxygen, and the singlet oxygen or reactive oxygen species kill the bacteria via oxidative damage. What they do essentially is that they attack the bacteria by multiple pathways simultaneously and disrupt the bacteria membrane. Now this is very different to an antibiotic. An antibiotic is like a needle. It will attack a bacteria in 1, 2, or maybe 3 pathways, And because it only attacks the bacteria through a small number of pathways, it is possible for the bacteria over time to develop resistance to the antibiotic. And that's why we're facing potentially an antibiotic crisis in the future, because we're not making very many new ones, and all the old ones are becoming less effective as the bacteria are evolving resistance. However, this lethal form of photosensitization which we're using for microbes, I think it's very, very difficult for them to evolve any kind of resistance, because literally we attack the bacteria by over 10,000 pathways simultaneously. And it can evolve for one or two, but to be able to have recovery to that kind of level, I think would be very, very difficult. So what we've done is made a whole series of antimicrobial surfaces, from keyboards through to pipes, which are being tested in food environments for antimicrobial, and also for photoactive and for superhydrophobic elements. These are some examples of the photosensitizer dyes that we use. So we've looked at things like methylene blue, crystal violet, and safranin O. Now, crystal violet actually has been approved by the World Health Organization as a topical antiseptic. And for those of you that are 50 or older, you may remember having a purple stain on your knee if you grazed it and your mum came and put on a tincture. That would have been crystal violet in the past. We have got other antiseptics now, but it was still used up until a few years ago as a medical emergency kit because it's very good at killing bacteria. But we've incorporated these dyes into our films and our paints. So what we've done is that we take the microscope slide and we incorporate it into some form of polymer. So these can be anything from acrylics through to polythene through to polysiloxane material. And what we found is if we also incorporate nanoparticles, and we've either done gold nanoparticles or we've done things like zinc oxide nanoparticles, when we've got the nanoparticles present, they can give a much higher lifetime for the excited state of the dye and a much better transference and generation of the reactive oxygen species. So we end up with materials which are very, very potent at killing bacteria. So this shows some examples of a UV vis spectra of the different wavelengths of our material which we've made. This shows what the color looks like for our crystal violet methylene blue nanogold paint solution. When we've made this material, the material has very, very little leaching into the solution, and so we think it's a surface contact phenomena which is responsible for killing the bacteria on the surface. So we've looked at this for destruction of Staphylococcus aureus and E. coli surfaces, and these are two of the most prevalent forms of problems within hospitals, especially the version of Staphylococcus aureus known as MRSA has caused a number of deaths in the UK and in a broader field. This here shows the number of bugs surviving on the surface. Now it says 100 here, but basically this was below our detection limit for the method which we use for detection. And this is our control. And this is what happens when we have 4 hours of illumination with quite a bright light source. This is about 3,500 lux. But that's not as intense as what you would get in an operating theatre, where you tend to have an illumination of the order of about 10,000 lux. So what we've seen here, so the higher up the bar is, the less bacteria are killed. But when we have crystal violet methylene blue gold nanoparticles with the light, we get virtually complete kill in the system for Staphylococcus aureus. And what was particularly exciting is we also get complete dark kill for the crystal violet containing samples as well. So the crystal violet samples are giving the same kill, the same antimicrobial properties of what you would have had on your, if you grazed your knee and your mum put on the old tincture on it. It still works in just the same way in the dark. Now, E. coli in the light, we're very, very good at being able to kill E. coli, but in the dark, E. coli is more resistant. But if we've done a longer time course experiment, and when you do this longer time course experiment, we were able to show that we could get kill with E. coli. Now, we've also gone on to measure a whole variety of other bacteria, and also for fungi as well, and viruses, and shown that these antimicrobial coatings work across a whole variety of instances, and we can have them working down to light levels as low as 100 lux, which is typically lower than what you'd get in a typical room lighting environment in the UK. Now, the number of bacteria or colony-forming units that we're using in these experiments is really, really high. It can be on the order of 1 million colony-forming units per centimetre squared, which is much higher than what you would observe naturally. And we've taken a number of the materials which we've made and we've left them in a UCLH hospital. So we have 20 keyboards in UCLH hospital which are coated with our antimicrobial keyboard. With our antimicrobial coating, so they're antimicrobial keyboards. These materials have also been used on things like lift buttons and pushes and bed rails, which are the major sources of contamination. So, in conclusion to this part of the talk, what I've talked about is antimicrobial dyes and incorporating them into surfaces. I've looked at dye localization at the surface and leaching, and lethal photosensitization for both Staphylococcus aureus and for E. coli, and shown that it works both in the light and also under dark conditions, which was a surprise. Now, from the first part of the talk on the superhydrophobic coatings, the key take-home message is to make a superhydrophobic coating, you need dual-scale roughness and some form of low-energy surface interaction with water. So that can be a polymer or it can be a lubricant. You can make the superhydrophobic surfaces very rugged by adding an underpinning layer of polymer or glue or even double-sided sticky tape if you like. And that gives them resistance to being squashed and to being rubbed off. And you can also convert those surfaces into a slip surface by adding a lubricant. And the lubricant layer tends to last for a very long time on the surface. It's not super hydrophobic, so you don't get the rolling motion of the water droplets on the surface, but it is repellent to virtually everything, both oils and water. But to get those surface, you need the underpinning surface roughness. So the main conclusion of the talk for these functional surfaces is to be able to get a functional surface, you need both surface roughness and a low energy coating. When combined together with a lubricant, you make slipped, and with an underlying adhesive layer, you make a material which is very resistant to abrasion and is very stable under a number of conditions, both high temperatures, low temperatures, acids and bases, and also to abrasion and mechanical attack. So with that, I'd just like to finish by thanking the organisers for letting me give my first ICAM lecture. I've never given one before. It's been a little bit of a strange experience for me. There is a small audience here in the wet of Manchester, but they've been very attentive. I'd like to thank Mr. Yao Lu, who was the student who did the majority of the work that I've talked about today. I also covered work from Sasha Neumark and from G. Byong. Professor Claire Colmalt, Dr. Sanjay Savastam, Caroline Knapp and Jemay Du all helped at one stage or another in this particular project. And I'd like to also thank you for your attention, and I'm happy to take any questions if there are any.